a presentation from Rinu Boney from Aalto University, and he will be talking about learning to play Clash Royale. So as always, you are welcome to ask the questions already during the presentation by writing those into the chat, and I will then read those aloud. And then after the presentation, of course, you can then open your mic and ask for to be able then to ask the questions by yourself. But without further speaks from me, so please, the floor is yours, Rinu.
Yeah. Hi. I'm going to talk about learning to play Clash Royale. I'm a PhD student at Aalto University, and this is work that I did as an intern at Supercell last year. Yeah, so this talk is based on this paper called Learning to Play Imperfect Information Games by Imitating an Oracle Planner, and it's available in arXiv if you want to know more about this work. And this work was done jointly with Alexander Ilin and Juho Kannala, who are my PhD supervisors, and also Jarno Seppänen, who is the machine learning lead at Supercell. So the practical motivation for this work was to design AI bots that can learn from self-play. And these kind of AI bots can be used in game design. For example, if you develop new content for the game, like new levels, then you can use AI bots to automatically test them, like find bugs or see how challenging these game levels are. And obviously, AI bots can be used as practice opponents, or single player games can be designed where humans play against bots. Or AI bots can be used to design tutorials so that new players can learn to play the game by playing against these AI bots. So this was the motivation to do this work. Besides the practical motivation, it's also interesting from a scientific perspective. I work on reinforcement learning, and one of the goals of reinforcement learning is to develop decision-making algorithms that can deal with complexities of the real world. So to do this, research in AI has focused on different kinds of games that emulate different kinds of these complexities. For example, in the game of, say, chess or Go, the agent has to discover complex playing strategies in a very large search space. In the case of poker, the agent has to deal with partial observability. In games like StarCraft or Dota, the agents have to act simultaneously in real time in very large action spaces. So what makes Clash Royale interesting is that Clash Royale has a unique combination of such complexities. So what is Clash Royale? Clash Royale is a very popular mobile game from Supercell. It's a multiplayer real-time strategy game. There are different modes in the game, but in this work we focus on just the two-player mode. For those familiar with game genre, Clash Royale is a unique game combining elements from collectible card games, tower defense games, and multiplayer online battle arena games. So let's see what a game of Clash Royale looks like. So in Clash Royale, every player has a collection of cards. You can collect these cards by playing the game and unlocking them. And the gameplay in Clash Royale consists of very short battles that last up to 5 minutes. To start a battle, you choose a deck of 8 particular cards from your collection, and then you start the battle. When you start the battle, you are dealt 4 cards from your deck. So here you can see your 4 cards. And how you play the game is that you can deploy these cards onto this battle arena. So you can just drag and drop them onto the battle arena. And as you can see, each of the cards has a particular elixir cost associated with it. And you have a particular amount of elixir with you. You can only deploy a card if you have enough elixir. So if you deploy a card, you deplete your elixir, it has to build up again before you can deploy more cards. Once you deploy a card, it follows predefined behaviors. So you don't do anything more to control them. And the goal in this game is to destroy your enemy's towers. So effectively using the elixir, effectively combining the cards, these are all important parts of the game strategy. Also, as you can see, you can only see your own cards. You don't know what the cards of your opponent are. You can only see them if the opponent deploys those cards into the battle arena. So you should also be able to predict and adapt to the opponent moves. So each battle can last for up to 5 minutes, but it ends instantaneously if the king tower is destroyed. If you destroy the king tower of your opponent, then you win the game. Yeah, so that's what a game of Clash Royale looks like. Let's look at some particular scientific challenges in learning to play this game. So firstly, it has a very dynamic, large and discrete action space. So in the whole game, there are around 100 different cards. And the battle arena is a 18 by 32 grid. So you can deploy these 100 cards into this 18 by 32 battle arena. So for the whole game, there's like 60,000 discrete possible actions. But you can see at a time, you only have 4 cards that you can deploy. So at a particular time in the game, the number of actions can vary from 1 to 2,305. So that's the actual action space when you play the game. And as I mentioned before, each card has a particular elixir cost associated with it, and you can only deploy cards if you have enough elixir. So the cards that you can deploy right now are called legal cards, and deploying them is a legal action. So if you don't have enough elixir, then there's only one action, that is just to wait. And depending on the number of cards that you have, the action space increases. As you can see, it's a fairly large action space. Another challenge is partial observability. As I said, you can only see your cards. You cannot see your opponent's cards. So the opponent has also chosen 8 cards when they start the battle. So this is a real-time game where humans play among themselves in real time around the world. So you are playing against somebody else who similarly chose 8 cards and started the battle. You're randomly matched with opponents around the globe. So your opponent, since you can't see the cards of your opponent can deceive you by choosing to hide certain cards until later in the game. This is similar to bluffing in poker. Another important challenge is exploration. So you can deploy a particular card only if you have enough elixir. Say at this point you deploy this particular card, then you would deplete all of your elixir. Then as the elixir starts building up, if you build up an elixir of 2, then a naive, greedy exploration strategy would choose to deploy this card because that's the only legal card. And then you would again deplete your elixir. And again, when it builds up, a greedy exploration strategy would deploy that again. So good exploration strategies have to intentionally wait for the costlier cards to become available. So you have to wait for a very long horizon of time if you want to explore a particular card later. Another challenge is cyclic strategies. So the cards in this game are designed such that each card can be countered with another card. So there's no single best deterministic strategy. In this case, learning algorithms can cycle around different policies without leading to better ones. So it can learn a particular strategy, then learn the counter strategy for that, then the counter strategy for that, and so on. So it could just keep cycling without converging towards better policies. So those are the challenges associated with Clash Royale. So let's look at the approach that we took in this work. We take a two-step approach to tackle this game. First, we build an Oracle planner, which has access to the full game state. From that, we train a follower policy that can play from partial observations by imitating the Oracle's actions. I'll explain this in detail now. So first, the Oracle planner with full observability. So think that you're in a particular state S in the game, and player 1 and player 2 receives their respective observations, O1 and O2. Then there are legal actions that player 1 can take and player 2 can take. So the goal of player 1 is to optimize its own actions so that it can win the game, and the goal for player 2 is to optimize its actions to win the game. So how the planner works is that when it's in a particular state, you start to plan. You initialize Q values for each action. So Q values mean the probability of winning by taking a particular action. So if this is the set of actions that player 1 can take, if this is the very first action, then this is the probability of winning by taking that particular action. And you just initialize it to 0.5 when you start to plan. After initializing this, the planner independently chooses the actions for both players. This is done using, in our work, an algorithm called Thompson sampling. This is a problem called multi-armed bandits. There are different algorithms to do this, and here we do Thompson sampling. Thompson sampling is a simple algorithm, and the basic idea is that you choose an action with the probability proportional to the probability that you win by taking that action. So you take actions that have a high probability of winning. To be more formal, you model this probability of winning using a beta distribution. So for every action, you maintain success counts and failure counts. In a game, if you took an action and if you won the game, you increase the success count. If you lost the game, you increase the failure count. And you can have a prior on the beta distribution. And how Thompson sampling works is that at each step, you sample from this beta distribution and then choose the action with the highest sampled probability of winning. So the planner does this for both players, and then you apply this action to the game simulator, and this leads to the next state. And again, in the next state, the planner initializes the Q values and chooses actions in that state. And this is repeated for a fixed number of steps called a planning horizon. And you reach a final state, S tilde. So you can do this till the end of the game, but that's very expensive. So to avoid that, you can approximate the probability of winning using something called a value function. So value function estimates the probability of winning for both players from this particular state, S tilde. There are different ways to implement a value function. You can learn value functions using machine learning, or you can use heuristics to design a value function. In this work, we use a simple heuristic function. So in Clash Royale, the player with the higher tower health is likely to win because the game is about destroying the towers. So the value function does a small rollout and then uses some heuristics like the tower health to determine who is likely to win. So the value function estimates who won the game or who would win the game, and now you can use this value estimate to update the Q values of all the actions that you took. So if player 1 won the game, then you increase the success counts of all the actions that player 1 took and increase the failure counts of all the actions that player 2 took. So this concludes one planning iteration. You can do many planning iterations. So if you do the next iteration, you would move down another trajectory, and similarly you use the value function and update the Q values of all the actions that you took. So you can do several iterations of this, and by doing this you would build a very large search tree of actions and their Q estimates. Finally, after many planning iterations, you can choose the actions with the highest Q estimates. So those are the actions with the highest probability of winning for both players. And you can apply that to the game. And you can update the root node of your search tree, discard the rest of the tree, and continue planning from there. So to kind of summarize, this Oracle Planner is kind of a procedure that you can call at any state, and it would produce the Q estimates of all the actions for both players. And you can apply the action with the highest Q values. So to those familiar with tree search algorithms, MCTS is a very popular tree search algorithm that's commonly used in games. So each iteration in MCTS is terminated when it encounters a novel sequence of actions. This is problematic in games with large branching factors. Like this is the search tree. If player 1 has like 100 possible actions and player 2 has 100 possible actions, then the branching factor of the tree is 10,000. And when you do MCTS, you would easily encounter new actions because the branching factor is so large. So if you terminate your iterations when you encounter new actions, you would end up spending a lot of time building the search tree. This is a problem. So in this paper, we do a very simple modification of MCTS that we call fixed depth tree search. So in fixed depth tree search, or FDTS, we do in each iteration, it's forced to continue for a fixed number of steps. So let's compare MCTS and FDTS. So this is MCTS, and if you build this kind of search tree, in the next iteration, you would start from the root node, choose child node, then here you encounter a new state. So you stop the termination and you use the value function to evaluate that, which is a random, could be a random rollout. And then you update the Q values. This is how MCTS tree would look like. So if you have a large branching factor and very large number of children, then you would spend a lot of time expanding the breadth of the tree rather than the depth. What we do in FDTS is that, so here you start from the root node, you encounter a novel state, but you don't stop there, you continue for a fixed depth. So here the tree is always expanded for a fixed depth. The advantage here is that if the tree search comes across a particular path which might be effective, then it can try out variations of the path towards the end, and it doesn't have to spend a lot of the time expanding the tree. So we compare this FDTS and MCTS algorithms in Clash Royale. We also use a simple baseline called Monte Carlo search, which is just random search. How we compare it is that we take Clash Royale and we use one planning algorithm for one player and another planning algorithm for another player, and it plays against each other. So you're playing one algorithm against the other. And as you can see, FDTS performs much better than MCTS, beating it like 96% of the time. I'm not going into more details about the planning algorithms. You can look at the paper for more details. So this Oracle planner that we described can be directly used in game design, like in the applications that I mentioned before, but it has two limitations. It requires a game implementation that should run much faster than real time. You may have to do tens or hundreds of planning iterations in each step, so the game implementation should run 10 or 100 times faster than real time. Also, the planner cheats by having access to the full game state, so it's not a fair opponent. So to overcome this, we have the follower policy, which can play under partial observability. So you can have a follower policy, which is a neural network. It can take an observation and directly predict the Q values of all actions. And you can train this by training it to imitate the Oracle planner. So the Oracle planner provides supervised labels to train the follower policy. This is called imitation learning. And so the direct way to do this is to collect data using self-play with the Oracle planner. So the planner plays against itself, and you collect a batch of data, use it to train the follower policy, and you repeat it. However, we found that this results in relatively poor performance. This is because the trajectories collected by the planner only contains good trajectories. What I mean by that is the Oracle planner is pretty good. So when it plays against itself, it only takes good actions. It never seeds a bad policy. So when the follower policy is trained on this data, it doesn't generalize to other kinds of policies. What we instead use is an algorithm called Dagger, which is a very common algorithm in imitation learning. What we instead do is that the data is collected using the follower policy, but then the Oracle provides training targets on those states. So if you think of learning to drive a car, the follower policy drives the car, and the Oracle planner later tells it what were the right actions that it should have taken. So to summarize our high-level approach, we have the game. You get partial observations from the game, and the follower policy network produces actions, and we take those actions in the game, but then the Oracle uses the full state of the game to compute better actions than the follower policy is trained to match the Oracle actions. So we test this in Clash Royale. So we use a fixed deck of 8 cards. Note that the whole game has lots of cards, and we use a very simple deck of 8 cards. And we test it against 3 baselines. One is just a random policy, then QMC is a model-free reinforcement learning baseline, and then human BC is a very strong behavioral cloning baseline. That's a fairly large neural network that's trained to imitate actions of human players from 76 million frames. And this particular AI agent has been used in production for almost 2 years. So it's a very strong AI bot. As you can see, the Oracle is able to beat all the other agents most of the time. This is because the Oracle is a very strong agent that actually cheats by having access to the full state. So it's an unfair AI bot. But the follower, which is a fair bot, that learns by imitating the oracle, that performs fairly well. It can beat the strong human PC baseline 71% of the time. Let's look at some strategies that are learned by during self-play. So the planner plays against itself. So here there's the red player and the blue player. Both of them are played by the planner. So this is a strategy that we call group of troops. So the red agent has played like two particular combination of cards. And first it played this giant card, which is a slow moving but very high damaging unit. Then behind the giant, it plays this card called Musketeer, which supports this card. So they jointly attack the tower. This is a very, very common strategy in Clash Royale.
So Rinu, there's a question in the chat. Can I
Yes.
read it now? Yeah.
Yeah.
So the idea behind Dagger versus imitation learning is that the Oracle planner will only ever go to states with a high value, whereas with the follower policy, you go to bad states and learn to copy the Oracle planner to get out of those bad states. Is that right?
Yes, exactly. So when you collect the data using the Oracle, you only visit those good states. But as the follower is trained, it's initialized with a random neural network. So as it trains, it visits a more diverse set of states. So you collect more rich data. That's the basic idea. Yes.
Okay, great, thanks.
Yeah. So when a player attacks with this kind of strategy, the best way to defend this is to attack the support unit first, because if you attack them together, it's hard to withstand that. So the best strategy is to attack the supporting unit, and the planner discovers that using self-play. But you see that the red player learned to counter that kind of attack. Another strategy is called hedging. So here the red player is attacking the blue player, but instead of defending it, the blue player chooses to attack on the other side. This can sometimes be an effective strategy. A particularly interesting strategy is race against time. So the battle lasts for up to 5 minutes. If the king tower of neither players are destroyed, then the game ends in a draw. So as the game starts to end, the players try to concentrate all of their resources and attack the king tower of the opponent. Yeah, those are some strategies that are discovered using self-play. So to test our approach, we also tested it on another game called Bomberman. Bomberman is a popular multi-agent reinforcement learning benchmark based on this classic game Bomberman. I'm not going to go into the details of the game, but it's a popular benchmark that we tested our approach on. And we get similar results that FDTS performs better than MCTS and Dagger performs better than simple naive behavioral cloning. So one of the limitations of our approach is called strategy fusion. So the policy network is trained to predict the average of Oracle actions from different states. Think that you're in different states, S and S dash, but you get same observations from those states. So in this case, the policy would predict exactly the same action, but the planner would provide completely different targets. But during training, the policy is trained to match both of those, so it kind of takes the average. And this might not be the best way to do this. It still works with this limitation, but it sometimes leads to instabilities in training the policy network. I'll end with an open problem, which is searching imperfect information or partially observable games. So in general, it's known to apply search algorithms to imperfect information games. The classic solution is to apply MCTS by randomizing the hidden information, but most game implementations do not support this. So this work is one way of sidestepping that, and simultaneous moves and large action spaces makes this very challenging. And this algorithm called counterfactual regret minimization has been very successful in poker, but it has not yet been applied to games with large state action spaces like Clash Royale. So I think that's a very promising line of future work in this area. Yeah, thank you for listening. So this is for me. Also, here's the project website where you can find the code for the Bomberman experiments and also a short video. Yeah, thanks.
So thank you, Rinu. So do we have now questions from the audience? So you can also open your mic if you wish and ask aloud. Okay, so when the others are still thinking, I could ask that what is now, you said that you are doing a PhD on the topic, so which is now the task that you are now concentrating on the first?
Yes, yeah. Sorry, I didn't understand.
Yeah, so which one? So you now stated few open questions on the field. So are you concentrating on one of those now in your PhD, or what is
Right.
your topic?
In my PhD, I'm focusing on model-based reinforcement learning, which means using a previously available model of the environment or learning a dynamics model so that you can do faster reinforcement learning. I have mostly been working on robotics problems where you learn dynamics models of robots. So in this game of Clash Royale, there's already an available model, which is the implementation of the game. So I haven't worked on this after the internship, but I'm generally working on this area of model-based reinforcement learning.
Yeah.
And this fits into that. Yeah.
Okay, great, thanks. So do we have questions from the audience then? Okay, yes, so there's now one. So do you, Ani, want to ask it aloud, or do you want me to
Sure.
read? Yeah.
Yeah, so can you expand on how this approach deals with the cyclical nature of the policies that you mentioned in one of the previous slides?
Yeah, it doesn't
Okay.
kind of address that. So in the whole game of Clash Royale, there are around 100 cards. So when you have many cards, this would be a very severe problem. In this work, we only considered a deck of 8 cards, so it's much less severe. So this is very initial exploration of using reinforcement learning into this problem. So we didn't solve the whole game of Clash Royale. So that was not a huge problem.
Yeah.
Yeah.
Okay, so more questions from the audience? Okay, so I guess everything was very clear so far, but thank you so much, Rinu, for very interesting presentation, and now I guess we can all then try to go and compete in the game and check how it's going.
Yeah, I encourage to play the game. It's quite fun and very short battles.
Yeah.
Yeah.
Okay, but great. Thank you, everyone, and then see you again next Monday in the Machine Learning Coffee seminar.
Thank you. Bye.
Thank you. Bye-bye.